Good morning, you guys. Today is Thursday, April 30th. It is the last day of April. So pretty exciting stuff, getting into May, kind of seeing the finish line here. Hopefully you guys are surviving okay with everything going remotely. Today we're going to get back into differentiating, okay? So getting away from graphing and plugging in points and stuff like that. And just basic exponent work, but getting back into like true calculus, so differentiating, okay? What we're going to look at is we're going to look at derivatives of exponential expressions. So what we have to understand right now is we've been working with derivatives of exponential terms for a very long time, okay? We know a lot about working with exponents and finding derivatives of exponential terms. Like for instance, what I want you to really consider right now is I have three basic exponential functions right here. Y equals x cubed, y equals 2x plus 1 cubed, and then y equals x to the 2x plus 1 power, okay? So really what it is these three things represent the difference between a term raised to a power, an expression raised to a power, and then a variable or an expression, or a term I should say, raised to an exponential expression. We're going to use these to kind of work our way back into a discussion about E. Okay, so what I guess I want to just kind of warn you of right now is this. I don't think your assignment is going to be too terribly difficult, especially given the fact that you just have to make sure that your answers match the back of the book. But there's going to be probably a lot of uncertainty today. You're going to probably get done with it and be like, well, that was easy, but I'm not sure if I did it right. And then you're going to check the back of the book and you'll be like, okay, I did it right. So it's going to be a little bit weird, but just bear with me here, okay? Because like I said, the assignment itself won't be too horribly difficult. All right, so let's talk about finding derivatives of these three exponential functions. The derivative of the first one is easy. We all know that to find the derivative of just a term raised to a power, you use the basic power rule. You bring the term out, or the power out front, the variable stays the same, and you subtract 1 from the exponent. That's it, right? The derivative of x cubed is 3x squared. We know how to differentiate. When it's an expression raised to a power, we have to apply the chain rule, which is the basic power rule. You bring the 3 down, you leave the expression 2x plus 1, and you subtract 1 from the exponent. But then you have to multiply that by the derivative of the inside, the derivative of the expression, which the derivative of 2x plus 1 is just 2, and then you clean that up, right? 2 times 3 is 6, so it's 6. 2x plus 1 squared would be the derivative there, okay? So we are very familiar with the basic power rule. We are very familiar with the chain rule. What I want you to see here is this. You do still do largely the same thing here, okay? When you have an exponent that itself is an expression, you still apply the basic power rule. So to find the derivative of this expression right here, the derivative of x to the 2x plus 1 power, you bring the exponent out front. 2x plus 1 times x. Okay, you bring the exponent out front, and then you subtract 1 from the exponent. So you do 2x plus 1 minus 1, which basically the plus 1 and minus 1 are going to cancel. It's going to be 2x as the exponent. But here's the thing that we really haven't talked about like this. When your exponent is itself a differentiable term, you have to then multiply your end term by the derivative of the actual exponent itself. So now here, and this is the particularly weird part, again, when your exponent is itself a differentiable function like this, you have to multiply it by the derivative of it. So what would be the derivative of the 2x plus 1? It would be obviously a 2. So this whole thing, this x would clean up to just x to the 2x power because the plus 1 and the minus 1 would cancel. And then you would take this 2 times, or distribute it essentially into this. It would be 2x times 2 is 4x, and then 2 times 1 is 2. So you could leave your derivative like that, or technically you could distribute this x to the 2x power in here, but then it's just going to get even murkier from there. So that's something that we really haven't encountered yet to this point, is what do we do when it's our exponent that's the differentiable function, not just like a function raised to a generic exponent. That's really weird, right? That was kind of hard to follow, right? The whole you bring the exponent down, you subtract 1 from the exponent, that's just the basic power rule. But then when your exponent itself is differentiable, you have to multiply the whole function by the derivative of the exponent. Okay, the reason that was so ugly and weird to work with is because the variable that we picked was just a generic variable x, okay? I talked to you guys last week about the fact that the number e is a considerably nicer base to work with when you're working with exponential functions, okay? And here's why, okay? The number e, okay, the number e is its own derivative. And here's what that means. If you have a function involving e, so if you take y equals e and I ask you to differentiate it, it is its own derivative. So y equals e, the derivative of that is y equals e also. So if you have something like this, y equals e squared. What's the derivative of y equals e squared? It's e squared. So this is going to really not make sense. It's not necessarily going to confuse you. It's just not going to make sense. Because what we're very familiar with is this. We're familiar with the fact that if you take a variable raised to the second power and you want to find its derivative, you bring the 2 down out front and you subtract 1 from the exponent. So if this was an x to the second power, the derivative would be 2x. That's true for any variable. But remember, e is not a variable. E is a number. Now that doesn't really clear things up either, because every one of us is like, well, if you pick any other number like y equals 3 and you want to find the derivative of that, the derivative of a number is 0, right? Okay, e is a very unique number because e itself isn't actually a value. Okay? If you think back to what we defined e to be, e is a limit, right? If we remember that e, the value of e is not a true actual number. It's the limit as x approaches infinity of the expression 1 plus x raised to the 1 over x power. So e is not an actual number. It has a numerical approximation, 2.718, but e by its very definition is not a true value. It is a limit. So the fact that e is a limit means that it doesn't basically fit, or it can bypass the rules of differentiating other numbers because it's not a true number. And it can also bypass all the rules for exponents on variables, which would be the basic power rule and the chain rule, because again, e is not a variable. So in a weird way, e is not a variable and it's also not a number, even though it has a numerical approximation, the 2.718. There's an explanation on page, what was it? I think 308. Yeah, there's an explanation on page 308 if you really want to kind of explore this deeper and try and figure out how exactly this makes sense. There is a proof for it that shows how e is its own derivative. So anytime you see a function involving e and you differentiate it, it doesn't change. It's just e, the derivative of e is e. The derivative of e squared is e squared. The derivative of y equals e to the x, the derivative of that is e to the x power, okay? The only thing that still does apply is the differentiable exponent part. Okay, so some of you are probably thinking to yourself, well, like, if every expression involving e is its own derivative, how are we even going to have problems today? Because again, e bypasses this, e bypasses the basic power rule, and e bypasses the chain rule. The only thing it does not bypass is this. So let me give you this. Do you guys remember how this was y equals x to the 2x plus 1 power? What if it would have been, let me bring it down here, y equals e to the 2x plus 1 power? Because what I told you last week, again, was that e is the ideal base to use, okay? E is a better base to use than just a variable x. Now, here's the thing. To find the derivative of this function, e to the 2x plus 1 power, we don't need to do the power rule. We don't need to bring the 2x plus 1 down and then do 2x plus 1 minus 1 because e is its own derivative. The derivative of this expression is the expression e to the 2x plus 1 power. The only part that still applies is once you differentiate, you have to multiply it by the derivative of the exponent. So all I have to do to this one is multiply it by the derivative of its exponent, which is 2. Just like we multiplied by 2 up here, but this is considerably easier. The derivative is 2e to the 2x plus 1 power. Okay? And like I said, your assignment itself is going to be pretty easy for you guys. I don't necessarily see you struggling tremendously with it. You're going to have some questions, and I'm fully prepared to answer them and have a clarification video tomorrow. I think we will, because I think you guys are going to have some questions. But it's going to be more murky than it is like, I'm totally lost. You're just going to be a little bit murky as to, I might have done it right, I might have done it totally wrong. But by its very nature of what e is not a true number and it's not a variable. That allows us, or it has these unique properties that it does not have to follow certain differentiation rules. So let me show you some examples of what your homework's going to be like, okay? Because I don't want this to go on forever here. Differentiate each, or whatever the directions are going to say, differentiate each. Okay, so here's the first one. First example, f of x equals e to the 3x power. We'll start with a simple one, just an e function, okay? E to the 3x power. The derivative is, you literally, the first thing you do to differentiate any e term is you rewrite it. It's e to the 3x. And then you multiply it by the derivative of the inside. So, or excuse me, the derivative of the exponent. So the derivative of 3x is 3, and then you clean it up. It's 3e to the 3x power. Okay? So it's kind of a bizarre thing, all right? You don't actually have to do anything with the e itself other than multiply it by the derivative of the exponent. Now, this is going to get murkier when we start adding things to this, okay? Or if we start potentially making our exponents uglier. So that's going to be the next one. I'm just going to switch to y's here to make things a little bit easier. Y equals e to the negative 2x cubed. Okay, so that's going to be weird because my exponent itself has an exponent in it. It's negative 2x cubed in an exponent. So I have e to a power, but my power has a power as well. So the first thing that we do to differentiate is we copy it down. E to the negative 2x cubed. But then we have to multiply that by the derivative. So this is kind of particularly weird because this is something that's differentiable. What is the derivative of negative 2x cubed? It would be negative 6x squared. And then if we start thinking about cleaning this up, okay, this is obviously this negative 6x squared could come out front, but if you think about it here, this is technically a negative exponent, which we probably shouldn't leave. We shouldn't leave negative exponents in our answers. So what I'm actually going to do is I'm going to take this e and move the whole thing down to the bottom. I'm going to leave the negative 6x squared on top, move the e to the bottom where its exponent becomes positive 2x cubed. And that's literally how we're going to leave this answer. Okay, like I said, murky is probably the best word I could use to describe how you're going to feel today. Okay, I want to show you two more examples without running super long here. Okay, so here's the next one. Y equals x squared e to the x. What I need you to understand now, or recognize now, is now we've added a variable to the mix. Okay, it's not like just putting a number out front. If you put a number out front, it's not a big deal. Okay, if you put a variable out front, now you have two separate expressions, x squared and e to the x. This is a product, which means its derivative requires a product rule. Okay, so the only rules that you're really allowed to bypass with e are the power rule and the chain rule. You still have to follow everything else, which includes the product rule. Okay. So if I do the product rule, it's the derivative of the first times the second. So the derivative of x squared is 2x times that by e to the x. Plus, the original first, which was x squared, times the derivative of the second. Well, the derivative of e to the x is e to the x. It is its own derivative, okay? And if we think about what we typically do with product rule, and again, murky's the name of the game today. Typically when we do product rule or quotient rule, we try and factor out whatever the two terms have in common, which in this case is e to the x, but they also have an x in common. So we could actually factor out an x and an e to the x. So this would be gone, this would be gone, we're left with a 2. This would be gone, one of the x's would be gone, and this is basically how you're the back of the, excuse me, I think the back of the book is going to leave your answers. X, e to the x, outside of 2 plus x. Last one real quick here, if we have time, just in case you run into one of these, y equals e to the x power plus e to the negative x power over 2. Okay? If there's one that you run into like this, where there's a 2 in the denominator or a number in the denominator, you can rewrite that, okay? Because we don't want to actually try and do quotient rule when we don't need to. You can pull the 1/2 out front, e to the x plus e to the negative x, and this is where things get really weird. If you think about this, to find the derivative of this, and you could if you really wanted to, you could distribute that 1/2 to make it less odd. 1/2 e to the x plus 1/2 e to the negative x. Make sure you can still see that. All right, what's the derivative of just this term, 1/2 e to the x? It's just an e, where its exponent is just an x, so the derivative of x would be 1. This is its own derivative. 1/2 e to the x is its own derivative. What's the derivative of 1/2 e to the negative x? It's almost the same thing. The only thing you have to do to this is you say the derivative of 1/2 e to the negative x is 1/2 e to the negative x times negative 1. So the only thing that changes is this plus sign becomes a minus sign because it's positive 1/2 times negative 1, which is negative 1/2 e to the x. Okay? The only thing you could do to maybe make it mesh with the back of the book is you could factor out the 1/2, so it would be 1/2 on the outside, e to the x minus e to the negative x. But yeah, you could also leave it like that. So I'm going to take a picture of this, make sure I attach it to your assignment on Classroom here. And like I said, some of them are going to be really easy. Some of them are going to be weird, especially when you get into, potentially product rule, quotient rule. But you're really just going to have to make sure you double check with the back of the book to make sure that things make sense. Okay? So do your best on it. Let me know what questions you want to look at tomorrow morning in the clarification video. And we will round out this week and get into May and hopefully have a nice weather weekend. All right, you guys. Have a great day. Talk to you tomorrow morning.